especially when I was one executive law because now when I choose above some leader, which even when the media side of translate products, but even on the same issues interests. My current is on their last profile in the line of see account of having it took me a minute, but I didn't realize that this I'm using using those it's kind of like whatever. It's um circle was this this other stuff where is not when circles something so this is understood not when the straight up your jump straight etc etc number four honest don't give not words on and sound from that book so on that note so the writings that one months consider recap well oh, but it also
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve search a 2D matrix. And I really like this problem because it's not one of those problems that you need a fancy trick for. You can actually solve this problem just by using logic. So we are tasked with creating an efficient algorithm for searching for a single value in an m by n matrix. The matrix has two properties. In every single row, the integers are sorted from left to right, and the first integer of each row, for example, this 10, is always going to be greater than the last integer of the previous row. So greater than this one. So in other words, we know that each row is sorted, and then the next row is going to be greater than that. So technically, each value in total throughout the entire matrix is going to be in sorted order. So that's pretty good. In this example, we were given a target 3, so if we search for the target, we will find it right here. So then we can return true that it does exist. If it does not exist, then we simply return false. So how can we solve this problem? The key word here is create an efficient algorithm. What would be the brute force? Of course, we could do an algorithm O of m by n, basically by searching every single value in the input array, right? That's a pretty easy algorithm to do on a two-dimensional matrix, but can we do better? Of course we can, because they gave us a couple properties that this matrix has some sorting already applied to it. Assume that we just had a single row, like forget that we had a matrix. If we just had a single row like this one, and we know it's in sorted order, do you know an algorithm that can search for a target value in a sorted array? I know of one called binary search, right? And how efficient is binary search? Well, let's say the size of this array is n, we could do a binary search in log n time, right? But of course, we know that we actually have m different rows, right? So let's say we ran a binary search on every single row until we found the input target value, right? What would the time complexity be? Well, log n multiplied by m is going to give us a solution like that. So that's using the first property, knowing that each row's integers are sorted. And this is a pretty good solution, but can we do even better than this? I'll give you a hint. We're definitely going to have to use this second property that they told us. Each row itself is actually in sorted order, as in we know that the values in this row are going to be smaller than all of the values in this row, and all of the values in this row are going to be smaller than all of the values in this row. So can we use that property to, instead of searching through every one of these m rows, maybe we can actually do a binary search just to figure out which one of these rows to search in the first place? Because, for example, if we're looking for a target value 3, let's take a look at this row. This row could have any values between 10, which is the lower bound, and between 20. So obviously the target value 3 is not going to fall within that range between 10 and 20, right? So then the question is, okay, if the target value is definitely not in this row, we can cross this row out. But then which direction are we going to go? Are we going to look at the row above it, or are we going to look at the row below it? Of course we would want to look at the one above, right? Because above, the top row is going to have smaller values than the bottom row, right? So when we cross this row out, we can also say that, let's cross this row out too, because of course this row is going to have greater values. That's how the binary search is going to work to even figure out which one of these m rows we're going to need to search, right? So we can reduce, instead of m, we can do a log m by running binary search. After we've ran that log m search, then we know, okay, this is the row that we have to do our second binary search on. So after we're done with that, we're going to do another binary search. So let's plus here log n, right? Log n for binary searching the row itself. So that's a better time complexity than we had previously, right? Log m plus log n. That's pretty dang good. So once we get to this row, we're going to say, okay, 3 is what we're looking for. Does that fall in the range between 1 and between 7? Of course it does. So either our target value exists in this row or it doesn't exist at all. So let's run binary search here. So of course we're going to have 2 pointers, left pointer and right pointer. Then we're going to check the middle value. In this case, I think the middle value is going to end up being this one because 0 plus 3 is going to become index 1. But let's just say it became this one just to kind of show you what it's going to look like. Let's say our middle value is here. We're going to check, okay, 5, is that 3? Nope, 3 is less than 5. So what we can do in our binary search is cross out these values, cross out our pointers. Now our right pointer is going to be over here. And let's say we ran binary search again. We compute the mid to be over here. We check, is this 3? Nope, 3 is greater than this. So we cross this out and we shift our left pointer over here. Left and right are both here. Middle is going to be here as well. We're going to see, okay, either this has to be 3 or nothing, or 3 just doesn't exist. Of course, this is 3, so we found it. We can return true, and that's the entire solution. So it's just a double binary search, and we can implement that pretty easily once you kind of know how to do binary search. And if you don't, I'm going to show you how to do it right now. So now let's get into the code. So the first thing I like to do is actually get the dimensions of the matrix. So let's get the rows and the number of columns in this matrix. We can do that pretty easily because we know for sure that the matrix is always going to be non-empty. And now we're going to do the first binary search. We're going to look for the row that we need to find. So I'm going to have 2 pointers, one for the top row and one for the bottom row. Top row is 0. The bottom row is going to be the number of rows minus 1. So now we're just going to continue to do the binary search until we can either find the target row or we figure out that the target row does not even exist in the binary search. So one case is that the target value is even greater than the largest value in this row. So let's go to that row. Okay, first, before I do that, let me actually compute the row. So we want the middle row. In this case, we'll take the top and bottom and divide it by 2. That's kind of how binary search usually goes, right? So, and then we have that row. So in our matrix, we're going to look at that row and we're going to look at the rightmost value. In Python, you can do that with -1, but we could also just do number of rows minus, or the number of columns minus 1, but in Python it's a little bit easier. So we're going to check, is this target value greater than the largest value in this row? If that's the case, what are we going to do? Well, then we need to look at rows with even larger values. So what we're going to say is our bottom row is going to end up being the current row plus 1, because now we want to look at rows that are larger than this row. Else, if the exact opposite happens, so let me copy and paste this, if the target value was even less than the leftmost value in the array, aka the target value was smaller than the smallest value in this row, in that case, we need to look at rows with smaller values. So we're going to shift our top pointer. Actually, I think I
어.
I just did it backwards. So when we look for larger values, we actually want to take our top pointer and then shift it down, because when you go down in the matrix is when you actually get larger values. And if we want to look for smaller, shift our top pointer. Actually, I think I just did it backwards. So when we look for larger values, we actually want to take our top pointer and then shift it down, because when you go down in the matrix is when you actually get larger values. And if we want to look for smaller values, we're going to take our bottom pointer and then shift it up. In that case, we would want to set it to be row -1. So that's the case if the target value was either too big or too small. If neither
Right.
of those evaluates to true, that means that the target value is actually does fall within this current row. In that case, we just want to break out of this while loop. And then we can do the second, want to break out of this while loop. And then we can do the second portion of the binary search. Now, it's possible that if we did not break out, maybe we just created an invalid condition where we figured out that the top and bottom pointers are invalid, right? Then our while loop would stop. And what that would tell us is that we crossed out every single row in the matrix and none of the rows contained the target value. In that case, we have to return false immediately. So basically, if not top is less than or equal to bottom, that means that none of the rows contain the target value, and then we can just immediately return false. If that's not the case, then we're going to move on to the second binary search portion, and we're going to run binary search on the current row that we found from the top and bottom pointers. So let me just copy and paste that. This is the row that we're going to run binary search on, and we're going to have a couple pointers left and right, which is going to be 0, and columns -1, because that's going to be the rightmost position in the row. And we're going to do pretty much the exact same thing that we just wrote above, a second binary search while left